Jupiter is the largest planet in our solar system, about 88,800 miles wide, or roughly 143,000 kilometers. From a backyard telescope, it looks like a bright bead, yet its true scale is planetary architecture. It has more mass than all the other planets combined, so its gravity quietly conducts nearby traffic. Volume tells another story. More than 1,300 Earths could fit inside. Such breadth invites deep atmospheres, and Jupiter answers with clouds stacked like endless horizons. It spins so quickly that it swells at the waist, becoming noticeably flattened at the poles. That shape reveals a world made mostly of fluid, not rigid stone, yielding to rotation's gentle insistence. Even its shadows feel spacious, because its moons cross a disk larger than any other planet's. In Jupiter, size is not decoration. It is the stage on which weather, magnetism, and time all perform. Jupiter is composed mostly of hydrogen and helium, the light elements that also dominate the Sun. Out beyond the early solar system's frost line, those gases were abundant and easy to gather. Jupiter's gravity collected them into a globe that never reached the heat and density needed for fusion. Near the top, hydrogen is a cold gas seasoned with ammonia, methane, and water vapor. Deeper down, pressure climbs until hydrogen becomes a dense fluid, and then a remarkable conductor. Scientists call that state metallic hydrogen, and it likely helps power Jupiter's magnetic field. Some models suggest a heavier central region, perhaps a diluted core mixed into the surrounding layers. Imagining a descent helps. Travel about 6,000 miles or 10,000 kilometers, and the rules of matter change. Jupiter shows how ordinary ingredients can become exotic under enough weight. In its depths, the periodic table learns new dialects. Jupiter rotates once in just under 10 hours, so a Jovian day is shorter than a workday on Earth. That fast spin is the metronome for its atmosphere, setting the tempo for winds and waves of cloud. Rotation creates an equatorial bulge because the planet is pulled outward at its middle. The equator stands about 5,600 miles, around 9,000 kilometers farther out than the poles. Rapid spinning also amplifies the Coriolis effect, bending moving air into long, steady jets. Those jets organize storms into bands that can last for years, sliding past one another like belts on a great wheel. Even lightning systems are carried along by the spin, stretched into traveling constellations of flash and shadow. Inside, rotation helps stir the conducting layers that generate magnetism. On Jupiter, hours are powerful. They shape the planet's very figure and its ceaseless patterned motion. Jupiter takes almost 12 Earth years to orbit the Sun, so its seasons unfold on a slow, spacious calendar. It travels at an average distance of about 484 million miles, roughly 778 million kilometers, where sunlight is faint. Because Jupiter's axis tilts only a little, the change from summer to winter is subtle compared with Earth. Still, the Sun's angle matters because it nudges temperatures and cloud chemistry across the globe. Jupiter's long year also sets the rhythm for its moons, whose eclipses and alignments drift with time. Ancient observers followed Jupiter's bright wandering and learned that the heavens had clocks of their own. Modern spacecraft still respect that pace, planning flybys around a planet that does not hurry. From that distant orbit, Jupiter often appears brilliant because its clouds reflect light efficiently. A far sun can still make a strong gleam. Jupiter reminds us that patience can be written into gravity. The Great Red Spot is a gigantic Jovian storm that has persisted for centuries, and still exceeds Earth in size. Early telescopes in the 1600s recorded a long-lived feature in roughly the same region, hinting at deep stability. Today, the spot is an anticyclone, a high-pressure whirl whose winds curve around the calmer center. It spans on the order of 10,000 miles across, about 16,000 kilometers, wide enough to engulf our planet. Power comes from surrounding jet streams that shear past it, feeding energy while also containing it. Its color likely arises when sunlight and charged particles transform ammonia-related compounds into reddish haze. The spot has been observed shrinking over recent decades, yet it remains a commanding presence. Smaller vortices sometimes spin nearby, like attendants orbiting a monarch. On Jupiter, storms can become landmarks. The red spot is weather that learned the art of endurance. Jupiter's bright zones and dark belts are bands of wind that encircle the planet in alternating directions. At first glance, they look like paint, but they are the visible edges of jet streams and rising air. In lighter zones, gases tend to rise, cool, and form higher clouds, while darker belts often mark sinking, drier air. Along their boundaries, winds can reach about 400 miles per hour, roughly 650 kilometers per hour. With no continents to block them, these jets can wrap all the way around the globe again and again. Embedded storms tug on the bands, and the bands tug back, trading momentum like neighboring rivers. Different cloud layers add subtle color, with ammonia ice high above and deeper mixtures below. The stripes are also a map of temperature, because rising regions tend to be cooler at the top. Jupiter wears its circulation openly. Those bands are the planet's handwriting across its own sky. Jupiter radiates more energy than it absorbs from sunlight, so it is warmed from within as well as from above. At its cloud tops, the temperature is about minus 230 degrees Fahrenheit, near minus 145 degrees Celsius, yet heat still rises from below. The main source is slow gravitational contraction, a long-term settling that releases energy as warmth. Another portion is leftover heat from formation, preserved in deep layers that cool only gradually. Convection carries that internal heat upward, making the atmosphere a restless fountain rather than a quiet lid. This extra energy helps drive strong winds and sustain long-lived storms, even where sunlight is weak. It also influences cloud chemistry, because warmer upwellings can lift water and ammonia to new heights. In effect, Jupiter is a planet with a low, steady hearth burning inside it. That hidden fire is gentle but persistent. It turns gravity into weather, and weather into a continuing story. Jupiter's magnetic field is the strongest of any planet, shaping an immense magnetosphere around it. Earth has a protective magnetic cocoon too, but Jupiter's is far larger and far more powerful. The field is generated by a dynamo deep within, where metallic hydrogen flows and conducts electricity. Rapid rotation and rising heat keep that conducting layer moving, like a slow global generator. On the sunward side, the magnetosphere can extend up to about 4 million miles, around 7 million kilometers. On the night side, it stretches into a long tail swept back by the solar wind. Within this region, charged particles spiral along magnetic field lines and can be trapped for long periods. Those particles create radiation belts and power brilliant auroras near the poles. Magnetism becomes a kind of weather in space. Jupiter's field shows how a planet can reach beyond itself without any visible arms. Jupiter's auroras glow steadily at its poles, and they can be far more powerful than Earth's northern lights. Like on Earth, the basic recipe is charged particles guided into the atmosphere by magnetic field lines. When those particles collide with gases, the gases radiate light, especially in ultraviolet and infrared. Jupiter adds a special ingredient, material from the moon Io, supplied by constant volcanism. Io's gases become ionized and form a plasma torus around Jupiter, feeding particles into the magnetosphere. Some of that plasma travels along magnetic pathways called flux tubes and rains into the polar sky. The brightest auroral ovals can span thousands of miles or several thousand kilometers around each pole. Juno and the Hubble Space Telescope have both observed these lights, revealing shifting arcs and hotspots. In Jupiter's case, moons help write the glow. It is a partnership between orbiting stone and a planet's invisible field. Jupiter has rings, but they are faint, dusty, and easily missed beside the planet's glare. Voyager 1 first revealed them in 1979, when backlit images showed a thin halo around the giant. Unlike Saturn's bright, icy rings, Jupiter's rings are made mostly of dark, tiny grains. Those grains are thought to come from small inner moons when micrometeoroids strike and loft dust into orbit. The main ring lies roughly 75,000 miles from Jupiter's center, about 122,000 kilometers, nestled close to the cloud tops in cosmic terms. Because the particles are small, sunlight and electromagnetic forces can subtly reshape the ring structure. Fainter components include a halo and gossamer rings tied to specific moons. The system is constantly being renewed and eroded, a slow exchange between moon surfaces and space. Rings do not always need brilliance to be real. Jupiter's are quiet evidence of motion grinding gently through time. Jupiter is orbited by over 90 known moons, and together they form a miniature solar system. Some moons are large and round, while many are small, irregular fragments captured long ago. The 4 Galilean moons, discovered in 1610, are bright enough to see as points with binoculars. Watching them shift night to night teaches a simple lesson. Not everything circles Earth. Each of the big 4 is a distinct world, shaped by tides, ice, or ancient impacts. Beyond them, distant outer moons travel in wide, tilted paths, like a scattered entourage. A useful scale is Io's orbit, about 262,000 miles out, roughly 422,000 kilometers, a span that still sits close to Jupiter's giant disk. Gravitational resonances link several moons, locking their rhythms together. Jupiter's moons are not mere accessories. They are chapters, each with its own geology and its own tempo. Io is the most volcanically active body in the solar system, and its eruptions are powered by tidal heating from Jupiter. From a distance, Io looks like a painted ball, but its colors come from fresh deposits laid by volcanoes. Jupiter's gravity flexes Io during every orbit, squeezing and stretching the moon repeatedly. That constant deformation creates frictional heat inside, melting rock and driving magma upward. Europa and Ganymede help by maintaining orbital resonances that keep Io's path slightly elliptical. Because the squeezing never becomes perfectly even, the heating never fades. Some eruptions shoot plumes hundreds of miles high, around 300 miles or about 500 kilometers. Those plumes feed gases into space, contributing material to Jupiter's magnetosphere. Io shows that gravity can be a furnace. It turns orbit into heat, and heat into a surface that is always being repainted. Europa probably contains a global ocean beneath its ice shell, making it one of the most promising places to look for habitable conditions beyond Earth. At the surface, Europa is bright and smooth, with long cracks and ridges that crisscross like seams in old ice. Few large craters appear, suggesting the surface is comparatively young and has been renewed. Jupiter's tides flex Europa and generate internal heat, helping keep water from freezing completely. Measurements of Europa's interaction with Jupiter's magnetic field also point to a conducting layer consistent with salty liquid water. The ice shell may be about 10 to 20 miles thick, roughly 15 to 30 kilometers, with an ocean below. That ocean could contact a rocky seafloor where chemistry has room to work. Plumes or surface exchange may occasionally bring subsurface material upward, though this is still being studied. Europa keeps its secrets under ice. It invites curiosity with the quiet confidence of a sealed, shining world. Ganymede is the largest moon in the solar system, spanning about 3,270 miles, or around 5,270 kilometers across. It is larger than Mercury, yet it orbits Jupiter like a loyal world within a larger kingdom. Ganymede's surface is divided between dark, heavily cratered terrain and brighter grooved regions. Those grooves hint that the moon once experienced tectonic motion in ice, reshaping parts of its crust. Most remarkably, Ganymede has its own intrinsic magnetic field, the only moon known to generate one. That field creates a mini magnetosphere embedded inside Jupiter's vast magnetic environment. Auroral observations suggest Ganymede may also harbor a subsurface ocean, because a salty layer can influence magnetic behavior. Inside, Ganymede likely contains differentiated layers of rock and ice, and perhaps liquid water between them. Ganymede is both moon and planet-like. It shows that even satellites can carry complex interiors and their own invisible shields. Callisto is a moon whose surface preserves a dense record of ancient impacts, making it one of the most cratered worlds known. Its dark ice and rock have remained relatively unchanged for billions of years, like a library that never closed. Because Callisto shows fewer signs of tectonics or volcanism than its siblings, many old craters still remain sharp. This makes it valuable for studying the early solar system, when debris was more common. The signature feature is the Valhalla Basin, a multi-ring structure stretching about 1,800 miles, roughly 2,900 kilometers across. Those rings are thought to be the frozen ripples of a colossal ancient collision. Despite its quiet surface, evidence suggests Callisto may still hide a deep subsurface ocean. If so, it would be an ocean sealed under time-worn ice, far from sunlight. Callisto teaches a different kind of beauty. It is the beauty of endurance, where history stays visible instead of being erased. Jupiter's immense gravity reshapes the paths of comets and asteroids, making it a major architect of the solar system's small body traffic. With a mass about 318 times Earth's, it can tug strongly on objects that pass anywhere near its neighborhood. Sometimes that pull captures a visitor temporarily, turning it into a brief companion before it departs again. Sometimes it redirects an orbit, changing where and when an object may travel in the future. A famous example is comet Shoemaker-Levy 9, which Jupiter broke and then drew into its atmosphere in 1994. The resulting dark scars on the clouds were larger than Earth, visible reminders of gravitational choreography. Jupiter's escape speed is about 37 miles per second, around 60 kilometers per second. a measure of its deep grip. Over long eras, such grip can both shield and scatter, depending on geometry. Jupiter does not chase. It simply bends routes, and the solar system quietly adjusts to the curve. Jupiter travels with Trojan asteroids that share its orbit in two great swarms, one leading and one trailing the planet. These bodies gather near gravitational balance points called Lagrange points, about 60 degrees ahead of and behind Jupiter. In those regions, the pulls of the Sun and Jupiter combine so that small objects can remain stable for millions of years. The swarms are not tight clusters, but broad clouds spread across large arcs of space. Thousands of Trojans are known, and many more likely remain too faint to catalogue. Some are tens of miles wide or tens of kilometers, and their dark surfaces suggest primitive carbon-rich material. Because they may preserve early solar system ingredients, they are attractive targets for exploration. NASA's Lucy mission, for example, was designed to visit several Trojans and study their diversity. Trojan asteroids are fellow travelers. They show that an orbit can have companions, not just a single lonely planet. Jupiter's radiation belts are so intense that they are among the harshest environments any spacecraft has ever faced. The belts form because charged particles become trapped by Jupiter's magnetic field and spiral along its lines. Particles are supplied by the solar wind and by moons, especially Io, which feeds material into the system. As the particles bounce and drift, they can reach high energies and repeatedly sweep through the same regions. This radiation can damage electronics, cloud camera sensors, and slowly degrade materials. Engineers respond with shielding and strategy, choosing orbits that minimize time in the worst zones. Juno carries a titanium vault to protect its core electronics, about 0.4 inches thick, roughly 1 centimeter. Even so, Juno's instruments must endure cumulative exposure with each close pass. Here, space itself becomes abrasive. Jupiter's belts reveal how magnetism can store energy, and how stored energy can become a surrounding sea. Jupiter produces powerful radio emissions that can be detected by antennas on Earth, making it a natural broadcaster of the outer solar system. These signals arise when energetic electrons interact with magnetic fields and generate coherent radio waves. One key process is the cyclotron maser mechanism, which converts particle motion into intense bursts near the poles. Some emissions fall in the decametric range with wavelengths of about 30 feet, roughly 10 meters. Observers have long noticed that many strong bursts depend on the position of the moon Io. Io supplies plasma to Jupiter's magnetosphere, and the magnetic connection between moon and planet helps trigger radio storms. To radio telescopes, Jupiter can sound like crackles and whistles translated into graphs. Those sounds are not atmospheric airwaves, but space plasma music shaped by fields and particles. Radio makes Jupiter present even when clouds hide detail. It is another way the giant announces its invisible dynamics. Jupiter's poles are capped by stable clusters of cyclones arranged in striking patterns, a discovery sharpened by the Juno mission. From Earth, Jupiter's poles are hard to see well, so earlier portraits favored the banded equator. Juno's close polar passes revealed a central cyclone at each pole, surrounded by several others in a ring. These storms persist because the balance of rotation, heat flow, and surrounding winds keeps them corralled. Individual cyclones can span thousands of miles, around 2,500 miles, or about 4,000 kilometers, comparable to continents. They rotate like great gears without easily merging, suggesting boundaries that act like invisible walls. Infrared views show warm cores and cooler edges, mapping motion in temperature as well as in wind. Over time, the polygonal arrangements can shift, but the overall structure remains surprisingly resilient. At the poles, Jupiter's atmosphere becomes geometry. It turns turbulence into pattern, and pattern into a calm kind of order. Jupiter has no solid surface, because its atmosphere thickens into fluid instead of ending in ground. The familiar stripes are only cloud tops, a high ceiling rather than a floor. Below, hydrogen and helium grow denser step by step. Gravity keeps that change smooth and continuous. A descent becomes a lesson in states of matter. Gas turns into a heavy, warm fluid as pressure climbs. Deeper still, hydrogen can become an electrical conductor, behaving like a strange metal. Without continents, down is not a place but a process. The planet's true body is layered by pressure, not paved by rock. Jupiter is a world where matter changes its manners gradually, and the journey itself is the landscape. Jupiter's average density is low enough that, in an imaginary ocean large enough, it would float. Its mean density is about 1.3 grams per cubic centimeter, around 80 pounds per cubic foot. That is only modestly denser than water, which is a startling comparison for a giant. The reason is composition, not emptiness. Hydrogen and helium are light ingredients, even when compressed. Yet Jupiter is massively heavy because it is enormous in volume. Deep inside, compression packs those light atoms tightly together. The upper layers remain more airy, like a vast sky that refuses to become stone. The numbers feel gentle, but the gravity is commanding. Jupiter proves that light materials, gathered at grand scale, can still make a powerful world. Jupiter's gravity at the cloud tops is strong, about 2.5 times Earth's, and it shapes everything that moves. The pull there is about 81 feet per second squared, roughly 24.8 meters per second squared. Rising air must work harder to climb. Sinking air gains speed as it descends. This helps organize tall storms and steady circulation into persistent patterns. Gravity also keeps the atmosphere bound despite rapid rotation and high winds. It presses gases into layers where chemistry changes with depth. It influences how quickly clouds billow and how firmly they settle back down. Even sound, if it could travel there, would meet denser air as it went lower. On Jupiter, gravity is a quiet sculptor with an enormous hand, shaping weather into lasting structure. Jupiter's visible clouds sit in layers, and each layer is a different chemistry expressed as weather. High above, ammonia ice forms pale tops that brighten the zones. Those bright regions often mark places where air rises and cools. Below, a layer linked to ammonium hydrosulfide can deepen color and contrast. Deeper still, water clouds can grow where warmth and pressure allow condensation. Condensing water releases heat that powers vigorous updrafts. The layers overlap rather than stack like shelves in a cupboard. Winds can shear them into ribbons, then fold those ribbons back into swirls. Sunlight paints the uppermost layer, while deeper layers shape the shadows. Jupiter's sky is a laboratory that chooses beauty as its display, and chemistry becomes scenery. Jupiter has lightning, and it flashes from storms powered by water hidden below the brightest haze. Spacecraft have recorded bursts that mark deep thunderclouds and vigorous updrafts. Moist air rises until water condenses into droplets and ice. That change releases heat, driving more rising motion in a self-feeding loop. The process is familiar, yet the scale is vast. Many flashes are linked to pressures of several bars, far above Earth's 1 bar sea level. 5 bars is about 73 pounds per square inch, or about 5 times Earth's surface pressure. 10 bars is about 145 pounds per square inch, or about 10 times Earth's sea level pressure. Lightning becomes a signpost pointing to water's hidden work. Jupiter's storms speak in light from the deep, and the planet's darkness answers with brief, bright signatures. Jupiter's moons cast shadows that slide across the cloud tops, creating eclipses and transits that feel like slow choreography. A large moon can pass between Jupiter and the Sun. Its shadow then sweeps across the planet for a few hours, turning bright cloud into temporary night. The dark circle moves over belts, zones, and swirling ovals. Contrast reveals texture that the eye might otherwise miss. Telescopes can time the shadow's path like a moving hand on a dial. The moon itself can appear as a bright bead on the limb. Sometimes a moon and its shadow travel together, a paired duet of light and darkness. These events helped early astronomers treat the sky as a clockwork system. Jupiter's weather becomes a screen for orbital rhythm, and the moons write their signatures across it. Jupiter's atmosphere keeps different time at different latitudes because the planet rotates differentially rather than as a rigid sphere. Near the equator, cloud features circle a little faster. At temperate latitudes, they lag by a few minutes. Astronomers therefore track more than one rotation clock. One is tied to the equatorial region. Another follows the temperate belts. Minutes sound small. Over many days, they shift storms noticeably from where you would otherwise predict. This is not confusion, but structure, made visible by drifting clouds. Jets and vortices carry their own pace as if each latitude owns a separate watch. Jupiter's winds measure time in local dialects, and those dialects together compose the planet's steady, rotating chorus. Jupiter hosts long-lived oval storms that can merge and evolve, creating vortices with distinct identities. One well-known example is oval BA, formed when several white ovals combined into one stronger anticyclone. Over time, it took on a reddish tint. That color shift earned it the nickname Little Red Spot. Its span has been comparable to Earth, around 8,000 miles across, or about 13,000 kilometers. Rotation helps it hold together, tightening winds around a calmer center. Surrounding jet streams act like rails that keep it corralled. The oval can brighten and dim as cloud heights and chemistry change. It is weather with a life story, not just a momentary squall. On Jupiter, even a storm can mature and change character, and the atmosphere keeps a memory in motion. Jupiter has infrared hotspots that act like windows into warmer layers beneath the top clouds. In visible light, they can look darker because reflective cloud cover is thinner there. In infrared, they glow because heat escapes more freely. A key window is near about 5 micrometers, roughly 0.0002 inches. At that wavelength, upper clouds become partly transparent. Warmth from deeper levels leaks upward like lamplight through gauze. The hotspots are not holes to a surface. They are gaps in the highest clouds, revealing deeper air currents and temperatures. Their positions and shapes shift with the surrounding jet streams. The planet offers different depths depending on the light you use. Jupiter's atmosphere is a layered lantern, and infrared lets you see the inner flame. The Galileo probe sampled Jupiter's atmosphere directly in 1995. turning distant bands into measured wind and chemistry. After entry, it descended for about 57 minutes. It sent back data until pressure and heat overcame it. Along the way, it recorded changing temperatures and strong winds. It reached pressures near 22 bars. That is about 320 pounds per square inch, and about 22 times Earth's sea level pressure. Instruments measured gases, cloud particles, and electrical activity. The probe's descent was brief, but its measurements still guide models today. It also reminded scientists that one entry point can be unusual compared with the global average. A single plunge can reveal both truth and local surprise. Jupiter answered with numbers gathered in the falling silence of a small, brave instrument. Jupiter's noble gases were found in unexpectedly high amounts, giving clues about the planet's cold beginnings. Galileo measured argon, krypton, and xenon in the atmosphere. These elements rarely react with other chemicals. They behave like time capsules. Their abundance suggests that very cold materials delivered them during formation. Icy grains can trap even reluctant gases at low temperatures. Those grains may have drifted inward and joined the growing planet. The result is a chemical fingerprint that points to conditions far from the sun or to especially cold building blocks. Noble gases do not easily lie because they do not easily change. Their presence is a quiet testimony preserved inside Jupiter's breath. In a planet of shifting clouds, these inert atoms still carry ancient news. Jupiter's jet streams extend far below the visible clouds, and Juno's gravity measurements helped reveal their depth. Juno's radio tracking detected tiny changes in speed during close passes. Those changes reflect tiny changes in gravity. Gravity, in turn, reflects where mass is moving inside the planet. Deep winds redistribute weight across broad latitudes. The results suggest that the familiar jets reach down about 1,900 miles, roughly 3,000 kilometers. Below that depth, the flow gradually blends into deeper layers that rotate more uniformly. The bands we see are therefore the surface expression of deeper motion. It is like watching waves and realizing the current goes far beneath them. Jupiter's stripes are not paint on top, but structure reaching downward. The atmosphere has roots, and those roots help explain why its patterns endure. Jupiter may have a diluted or fuzzy core, meaning heavy elements could be spread outward instead of locked into a compact center. Traditional pictures imagine a neat, rocky ball at the middle. Newer models allow a gradual blend. Dense material may mix into surrounding metallic hydrogen. This can fit measurements of Jupiter's gravity and interior structure. It also changes how formation is imagined. Early impacts could have stirred the deep interior. Intense convection could have mixed layers over long spans of time. In this view, the core is more like a region than an object. The planet's center becomes a slow gradient, not a sharp border. Jupiter's heart may be a misty boundary rather than a hard kernel. Even in the deep, the giant prefers smooth transitions to abrupt walls. Jupiter's thermosphere is warmer than simple sunlight predicts, showing that energy moves through the planet in subtle routes. High above the main clouds, the air becomes thin, yet it can still be heated from within and from above. Auroral processes deposit energy near the poles. Winds can carry some of that warmth around the globe. Meanwhile, storms and jet streams can launch waves upward. Those waves can break and release heat at high altitude. The result is an upper layer that runs hotter than distance alone would suggest. It is a reminder that a planet is not warmed only by the sun. Motion itself can be a furnace when guided by rotation and magnetism. Jupiter's high air is a quiet furnace fed by invisible currents. The planet keeps warmth aloft the way a sea keeps swell, by passing energy along. Jupiter's upper atmosphere glows with the trihydrogen ion, nicknamed H3+, and that glow helps map the planet's high winds. Ultraviolet light and energetic particles can create H3+ from hydrogen. The ion then radiates in infrared wavelengths. Telescopes and spacecraft observe that emission as shifting patterns. Brighter regions often trace where auroral energy is being deposited. Subtler variations reveal winds that transport heat sideways. In this way, H3+ becomes a lantern carried by the atmosphere itself. The glow is invisible to human eyes, yet it is steady in instruments. It turns chemistry into a kind of weather map. It also links Jupiter's magnetosphere to its air, showing how space and atmosphere converse. Jupiter's chemistry turns invisible motion into measurable light, and the sky becomes readable. Jupiter's colors come from chemistry and sunlight working together, and the planet wears those reactions like slow-moving art. High ammonia clouds tend to look pale and creamy. They brighten zones where air rises and cools. Deeper materials darken belts where air sinks and dries. Trace compounds involving sulfur or phosphorus can tint regions with warm browns and oranges. Ultraviolet light can break molecules apart. The fragments recombine into more complex pigments, often grouped under the name chromophores. Those pigments act like dyes suspended in air, changing the planet's palette without changing its shape. Color can also shift as storms loft material upward, or as sunlight alters it over time. Jupiter is a living painting refreshed by light and motion. The hues are not decoration, but chemistry made visible, and the atmosphere wears its reactions proudly. Jupiter's cloud tops are patterned with waves and ripples that reveal atmospheric gravity waves, not the cosmic kind discussed in relativity. A stable layer can be disturbed by storms or wind shear. Buoyancy then tries to restore balance. The atmosphere responds with oscillations that travel. These waves can shape scalloped edges along belts. They can also form long, faint ripples across bright zones. Some patterns stretch hundreds of miles or hundreds of kilometers before fading. The waves carry energy without carrying material far, like a ripple on a lake. They hint at hidden layers that resist vertical motion and then rebound. In photographs, they look like fine stitching across the planet's fabric. Jupiter's waves show that even turbulence can produce elegance. The planet hums softly in pattern, and the camera catches the melody as ripples in cloud. Jupiter's inner moons help sustain its faint rings by supplying fresh dust, turning small impacts into lasting structure. Meteor and Adrastea orbit close to the planet. Micrometeoroids striking them can knock loose grains. Those grains drift into ring-shaped paths around Jupiter. Farther out, Amalthea and Thebe contribute to broad gossamer rings. Their dust spreads into ghostly sheets shaped by gravity and electromagnetic forces. Amalthea itself is irregular and reddish. It is about 155 miles long, roughly 250 kilometers, small enough to feel like a mountain made into a moon. The rings are therefore not ancient monuments, but ongoing exchanges between surfaces and space. Dust is created, carried, and replaced in a continuing cycle. Jupiter's ring system is quiet, yet constantly being rewritten. Even the smallest moons can leave lasting signatures when a giant's gravity holds the ink in place. Jupiter's mass shifts the solar system's center of mass. making the Sun perform a gentle wobble around a shared barycenter. Because Jupiter is so heavy, the barycenter can lie outside the Sun's surface. The Sun and Jupiter both orbit that shared point. The Sun's loop is smaller but real. The motion is slow and steady. It is one reason the Sun is not perfectly still in space. In measurements, the barycenter can sit about 460,000 miles from the Sun's center, roughly 740,000 kilometers. That distance is comparable to the Sun's own radius, so the shared balance point can hover near the edge of the solar furnace. This is gravity as choreography on a grand stage. A planet's pull can gently guide a star's path without dimming its light. Jupiter reminds us that mass writes music into orbits, and even the Sun keeps time to that tune. Jupiter may experience helium rain deep inside, a process that could help maintain internal warmth over immense spans of time. Under extreme pressure, helium can become less willing to mix with metallic hydrogen. It may separate into droplets. Those droplets would sink through deeper layers. As they fall, they release gravitational energy as heat. Over billions of years, small effects can accumulate into significant warmth. Helium rain could also influence how helium is distributed in the upper atmosphere. The idea is not a storm you would see from above, but a slow sorting process hidden in depth. It is matter choosing new partnerships under pressure. In that hidden rain, Jupiter's interior keeps generating gentle heat while remaining dark and calm. The planet's warmth may be fed by droplets falling through darkness, turning gravity into a quiet, enduring hearth. Many of Jupiter's outer moons are irregular objects that were likely captured, not formed beside the planet. They wander far from the bright, orderly Galilean moons. Many travel on tilted paths, and several even orbit backward, a strong clue of capture. In the young solar system, gas and collisions could bleed away energy and allow capture to succeed. Once trapped, these moons often broke into groups, like a shattered visitor becoming a family. Some members share similar inclinations and cluster in orbital space. Many circle Jupiter more than 12 million miles away, about 20 million kilometers. Their distant paths make them sensitive to the Sun's pull as well as Jupiter's. Over time, collisions can grind them down and reshape the groups. Their small sizes make them faint, yet their orbits preserve ancient history. These outer moons are fossils in motion. They show Jupiter as a collector as well as a ruler. Io, Europa, and Ganymede are locked in the Laplace resonance, and that repeating rhythm keeps their interiors warm. The three moons do not drift freely in time. For every 4 orbits Io makes, Europa makes 2, and Ganymede makes 1. This cadence prevents their orbits from becoming perfectly circular. Slight eccentricity means Jupiter squeezes them unevenly each lap. The constant flexing turns motion into internal heat. On Io, the tidal bulge can rise and fall about 300 feet, roughly 100 meters. Heat dries volcanoes, which repaint the surface in fresh colors. On Europa and Ganymede, flexing helps maintain liquid layers beneath ice. The resonance has likely persisted for billions of years, keeping the beat through changing ages. Resonance is a gravitational song that never quite ends. It shows how orbits can become engines powered by time itself. The Galilean moons are tidally locked, so each one keeps nearly the same face turned toward Jupiter. Tidal locking begins with an ordinary spin. Jupiter's gravity raises tides in a moon's body, and flexing wastes energy as heat. Over long time, the rotation slows into a stable match with the orbital period. A near side becomes familiar, and a far side becomes private. This is why Jupiter hangs in the same place in Europa's sky. Yet the locked moons are not rigid statues. Europa's surface may rise and fall about 100 feet, around 30 meters, as tides flex its ice. That flexing can open cracks and help shuffle surface materials. On Io, locking helps define a leading and trailing hemisphere with different radiation exposure. The moons keep one face to Jupiter, but they still change under its pull. Even steady orientation can accompany deep, rhythmic motion. Jupiter's axis is tilted by only about 3 degrees, so its seasons are gentler than Earth's. A small tilt means the Sun's overhead point does not wander far north or south. Earth's larger lean drives pronounce seasonal contrasts, but Jupiter stays nearly upright. Even so, sunlight still shifts with the planet's long orbit and mild tilt. At solstice, the subsolar point sits only about 2,300 miles from the equator, roughly 3,700 kilometers. That is a modest migration across a globe of immense circumference. The small tilt also suggests a calmer history of large obliquity-changing impacts than some worlds endured. Subtle seasonal changes can still influence upper hazes and temperatures. A faint adjustment in sunlight can alter how aerosols form and fade. Jupiter's weather is powered strongly from within, so seasons are an accent rather than a conductor. The planet keeps its posture steady as it circles the Sun. In that steadiness, Jupiter shows how a world can be dynamic without dramatic seasonal swings. Jupiter's atmosphere can be dry in places, and the Galileo probe fell into a cloud-poor hotspot that showed how uneven the planet can be. From a distance, the bands look like uniform layers of cloud. Up close, circulation divides the sky into rising zones and sinking belts. Where air sinks, it warms, sheds moisture, and clears. These clearings glow in infrared because deeper heat can escape. Many hotspots span about 1,000 miles, roughly 1,600 kilometers, wide enough to be tracked over time. Galileo entered one such region, so its measurements sampled an unusually dry column. That taught scientists to be cautious about treating a single descent as global truth. Hotspots also reveal how jet streams sculpt cloud cover into openings and curtains. Even on a giant, weather has neighborhoods with distinct character. Jupiter's atmosphere is not a uniform blanket. It is a woven fabric with thin places and thick places, stitched by motion. Comet Shoemaker-Levy 9 struck Jupiter in 1994, and the resulting scars became a rare tracer of Jovian winds and chemistry. Jupiter had already torn the comet into a string of fragments. Over several days, those fragments plunged into the atmosphere and vanished from sight. Each impact launched a rising plume that lofted material into higher layers. Dark debris spread out and formed blotches that drifted with the planet's jet streams. Some marks stretched more than 7,000 miles across, about 11,000 kilometers. As the debris moved, it outlined wind patterns like ink in water. The impacts also introduced new chemicals and heated pockets of the upper atmosphere. Observers watched the scars fade as particles settled and sunlight altered them. The event linked small icy bodies to the dynamics of a giant atmosphere. Jupiter became a natural laboratory, briefly marked by cosmic visitors. Those fading stains were not just spectacle. They were data written across clouds. Jupiter's birth story is central to planetary science, because giant planets shape what smaller worlds can become. One leading idea says a solid core formed first, and then pooled in gas rapidly. Another idea suggests parts of the young disk collapsed directly under their own gravity. Jupiter's heavy element content and interior structure are used to test these pictures. Either way, the planet formed where cold allowed ices to survive and add mass efficiently. In the early disk, that cold could mean temperatures around -330 degrees Fahrenheit, near -200 degrees Celsius. Ices and rocks together provide the seeds that gravity can enlarge. As Jupiter grew, it likely influenced how material was distributed across the disk. Its growth could have redirected planetesimals and altered where other planets acquired ingredients. Formation models also try to explain why Jupiter is enriched in some elements compared with the Sun. Jupiter is a record of assembly, written in chemistry and structure. The planet stands as a witness to the disk that once surrounded the newborn Sun. In its origin, the solar system's architecture begins to take shape. The amount of water inside Jupiter is a key measurement, because it links the planet's chemistry to its birthplace in the early solar system. Water carries oxygen, and oxygen tracks how many solids join the growing giant. Jupiter's upper clouds are dominated by ammonia, which hides the deeper water layer. The main water cloud region is expected far below the visible tops, where pressure is higher and air is warmer. Many models place that layer roughly 60 miles down, about 100 kilometers. Thunderstorms can punch upward from those depths and carry signatures of water to higher altitudes. Microwave observations help by sensing thermal emission through clouds. Interpreting those signals requires understanding how ammonia, temperature, and motion combine. Water abundance also matters for comparing Jupiter with exoplanet giants. It helps reveal whether Jupiter formed from especially icy building blocks or from a different mix. A single molecule becomes a storyteller for a whole formation history. Jupiter's water is hidden, but it is not silent. It waits in the deep as a clue about the planet's earliest days. Jupiter's stratosphere contains hazes born from sunlight, and those hazes drift and brighten as chemistry and auroras reshape them. Above the churning weather layer, the air thins and becomes more stable. Ultraviolet light breaks methane molecules apart high in the atmosphere. The fragments recombine into more complex hydrocarbons, some of which condense into fine particles. This haze can be patchy, forming belts and caps that do not match the clouds below exactly. Temperatures here can be around 110 kelvins, near -260 degrees Fahrenheit, or -160 degrees Celsius. Auroral energy near the poles adds extra heating and changes chemical pathways. Waves from below can propagate upward and modulate the haze like ripples in a veil. Because the stratosphere is thinner, small changes can travel far before fading. Studying these hazes helps connect sunlight, magnetism, and atmospheric circulation. Jupiter's upper air is not empty. It is a quiet workshop where photons build new molecules. The planet wears that chemistry as a faint, shifting crown above its storms. Jupiter has helped send spacecraft to the outer solar system by providing gravitational assists that add speed without using much fuel. A flyby is a dance with gravity rather than a push from engines. The spacecraft approaches, curves around Jupiter, and departs on a new path. In the Sun's frame, it can leave faster by borrowing a trace of Jupiter's orbital momentum. The planet loses an immeasurably small amount, while the spacecraft gains a great deal. Voyager 1 used this technique to reach Saturn and then continue outward. After Jupiter, Its speed was on the order of 35,000 miles per hour, about 56,000 kilometers per hour, relative to the Sun. The same principle aided Voyager 2 on its grand tour of the outer planets. New Horizons also used Jupiter to bend and quicken its route toward Pluto. Gravity assists turn a planet into a gate and a guide. They make exploration feel like sailing on invisible currents. Jupiter, with mass and motion, becomes a generous source of momentum for travelers. Pioneer 10 and Pioneer 11 were the first spacecraft to visit Jupiter, and they measured the giant in ways telescopes could not. Before them, Jupiter was mostly a disk and a set of guesses. Pioneer 10 flew by in 1973 and returned the first close-up images of the banded clouds. Its instruments sampled the radiation environment and found it far stronger than Earth's. Pioneer 11 followed in 1974 and refined measurements of the magnetosphere and particle belts. These early readings shaped how later missions were engineered and shielded. Pioneer 10 passed within about 82,000 miles of the cloud tops, roughly 132,000 kilometers. That close approach provided strong signals for magnetometers and particle detectors. The flybys also improved estimates of Jupiter's mass distribution through tracking. They glimpsed moons as worlds rather than points of light. These missions were small by modern standards, yet their impact was large. They opened Jupiter as a destination for physics, not just a target for photographs. In their brief passes, the first visitors turned curiosity into measured reality. Jupiter's deep rotation is best traced by its magnetic field and radio pulses, because clouds at different latitudes move at different speeds. The visible stripes are a restless surface of motion. Timing a cloud feature can yield a rotation that belongs to the wind, not the interior. Radio emissions tied to the magnetic field provide a steadier clock. That clock reflects the rotation of the conducting region, where the dynamo lives. Astronomers use it as a standard reference, often called System 3. The period is about 9 hours and 56 minutes, a rapid spin for such a large world. Fast rotation helps organize jet streams and maintain long-lived vortices. It also contributes to Jupiter's equatorial bulge and overall shape. At the equator, the implied surface speed is enormous, around 28,000 miles per hour, about 45,000 kilometers per hour. That speed is not a wind you feel, but the planet turning beneath its own sky. Jupiter's rotation is a hidden heartbeat, best heard in radio rhythms. The clouds may wander, but the interior keeps time with steady insistence. Jupiter's storms may form slushy hailstones called mushballs, and those mushballs could help move ammonia and water between layers. The visible cloud tops are rich in ammonia, yet some observations show ammonia depleted in certain regions. One explanation is transport by storm-driven particles. In powerful thunderstorms, water ice can mix with ammonia and liquid water under high pressure. The mixture can freeze into soft pellets that grow as they tumble in updrafts and downdrafts. Some may reach about 2 inches across, roughly 5 centimeters, before falling. As they descend, they carry ammonia into warmer depths, where the slush melts and releases it. This process would redistribute ammonia vertically and laterally. It also ties lightning-rich storms to chemical patterns seen from space. Mushballs are a reminder that condensation is not always gentle snowfall. On Jupiter, precipitation can be complex, layered, and dynamic. The atmosphere becomes a conveyor, with storms as the machinery. In those falling pellets, chemistry and weather cooperate to reshape what telescopes see. Himalaya is the largest of Jupiter's irregular moons, and it leads a small group that shares a similar orbital neighborhood. Unlike the Galilean moons, Himalaya is not a round, ocean-bearing world. It is a captured-looking body with an uneven shape and a darker surface. Its orbit is far beyond Callisto, where Jupiter's pull still dominates, but the Sun's influence begins to matter. The Himalaya group likely formed when a captured parent body broke apart. Members then continued on related paths, like fragments keeping a shared drift. Himalaya itself is about 105 miles across, roughly 170 kilometers. That size makes it a significant landmark among irregular satellites. Studying its light and spectra helps infer surface materials and possible origins. Its distance and inclination preserve information about early capture conditions. Small moons can also collide, reshaping the group over time. Himalaya is a reminder that Jupiter's system includes both grand worlds and rugged remnants. The giant planet holds not only perfected spheres, but also rough pieces of ancient debris. In these irregular moons, capture and collision remain visible in orbit. Jupiter often becomes the brightest planet in the night sky after Venus, and its brilliance comes from size, distance, and reflective clouds. Even far from the Sun, Jupiter presents a huge disk to incoming light. Its pale upper clouds scatter sunlight efficiently, especially in bright zones. When Earth and Jupiter align well, the giant comes relatively close and grows strikingly bright. At favorable oppositions, it can be about 365 million miles away, roughly 590 million kilometers. That closeness enlarges its apparent disk and boosts its brightness noticeably. The planet's albedo is shaped by clouds of ammonia ice and other hazes that reflect light. Dark belts reduce reflectivity locally, but the overall globe remains bright. Even modest binoculars can reveal its 4 largest moons as small companions. Because Jupiter is so large, it can keep a strong presence even when it is not at its nearest. Its steady glow helped ancient observers track planetary motion against the stars. Jupiter's brightness is a physical consequence of clouds and scale. In the night sky, it becomes a lighthouse powered by sunlight and distance. Jupiter's tropopause is a boundary where the temperature trend changes, marking a shift between stormy lower air and calmer upper layers. In the troposphere below, rising gas expands and cools, and clouds condense into weather. Convection there carries internal heat upward like a slow boiling. As you climb, the cooling eventually slows and reaches a minimum. Near this boundary, temperatures can be around -235 degrees Fahrenheit, about -150 degrees Celsius. Above the tropopause, the stratosphere begins, where temperature can rise again and chemistry becomes more influential. This change affects how waves travel and where hazes can form. The tropopause can act like a lid, keeping much of the turbulent mixing beneath it. Yet strong storms and atmospheric waves can still punch information upward. Understanding this boundary helps explain why some features stay confined to certain layers. It is a quiet border drawn by physics, not by geography. Jupiter's atmosphere is a stacked kingdom, and the tropopause is a key gate between realms. In that gate, the planet's weather hands off to its upper air chemistry. Jupiter's equator hosts a strong eastward jet that can exceed 300 miles per hour, about 500 kilometers per hour, and it helps organize the planet's banded appearance. The equator is where the Coriolis effect weakens, changing how storms and waves behave. Waves generated by convection can travel and interact in ways that funnel momentum toward low latitudes. Over time, that momentum helps maintain a swift ribbon of air. The jet forms a boundary that influences where belts and zones begin and end. It can also shepherd vortices, guiding them along preferred tracks. Because there is no solid surface, the jet is shaped by pressure gradients and deep circulation rather than landforms. Juno's gravity data suggests that many jets extend far beneath the visible clouds. The equatorial flow interacts with neighboring jets, creating shear that can spawn turbulence and small storms. In some images, the equator shows bright plumes and dark patches, signatures of rising and sinking air within the fast flow. The jet is both highway and barrier in a fluid world. It shows how rotation can sculpt atmosphere into enduring architecture. On Jupiter, the equator is not quiet. It is a swift, persistent current encircling the planet. Jupiter's two hemispheres share the same basic stripes, yet their differences help scientists test ideas about rotating atmospheres. At first glance, the planet seems symmetric, like a mirror in cloud. With careful watching, subtle imbalances appear in the width and color of certain belts. The Great Red Spot sits in the south, while the north hosts its own persistent vortices and complex wave patterns. Storm outbreaks can favor one hemisphere for years and then quiet down. Internal heat, sunlight angle, and the history of merging storms can all contribute. Because the bands wrap a vast circumference, about 275,000 miles or roughly 440,000 kilometers, small percentage changes still span enormous distances. Tracking such differences requires long records and consistent measurements. These asymmetries help refine models of jet stability, convection, and chemical haze production. They also warn against assuming a single average Jupiter at any moment. The planet's global pattern is steady, but its details are alive. In those north-south contrasts, Jupiter reveals the quiet complexity of rotating fluids. Even a giant can have subtle preferences written in cloud. Jupiter sends out fast dust streams of tiny grains, accelerated by electromagnetic forces in ways that gravity alone cannot explain. Spacecraft have detected these grains as brief clusters of impacts, like a sandstorm passing through the dark. Many grains likely originate near Io and the inner moons, where micrometeoroid strikes and fresh debris supply raw material. Io's activity adds dust to this region, keeping the source renewed. Sunlight and surrounding plasma charge each grain electrically. Once charged, a grain responds to Jupiter's rotating magnetic field and the electric fields it generates. Those forces can sling dust outward on paths that look impossible in a purely gravitational map. Some streams travel well over 100,000 miles per hour, more than 160,000 kilometers per hour. Their intensity can rise and fall as Jupiter turns and as the solar wind presses on the magnetosphere. Dust streams reveal that Jupiter's space environment can behave like a natural particle accelerator. They connect small moons to far distances with threads made of moving specks. In those tiny travelers, the giant's invisible forces become visible in data. Juno has been orbiting Jupiter on a polar track since 2016, giving scientists their clearest look at the giant from pole to pole. The mission was designed for brief, close encounters, rather than long exposure. Jupiter's radiation belts are fierce, so Juno dives in and then retreats. At its closest, it passes roughly 3,000 miles above the clouds, about 5,000 kilometers. From that vantage, its instruments listen to gravity's tiny tugs and magnetism's deep hum. A microwave radiometer peers through cloud layers to sense temperatures and ammonia below. Gravity tracking reveals how winds extend downward beneath the visible bands. Magnetometer readings map a field that is both strong and strangely detailed. Each close pass is a swift sampling of a vast world. Juno turns Jupiter into a portrait made of measurements. The planet feels less like a distant disk and more like a living structure. Jupiter's south equatorial belt can fade until it nearly vanishes, then revive in a planet-wide transformation that changes the face of the giant. For months, a dark band may turn pale as higher. Brighter clouds spread over it like a fresh veil. The belt is still there in motion and chemistry, but its usual layer is hidden from view. Eventually, vigorous storms break through, opening dark rifts that expand and stitch the belt back together. The revival can launch bright plumes and turbulent curls that spread longitudinally around the planet. The process is a reminder that Jupiter's appearance is a slice through layered clouds, not a painted surface. Observers on Earth can follow these changes with modest telescopes, watching a familiar stripe return as if re-inked. Each fade and revival is weather acting on a grand canvas. A belt can hide beneath bright clouds, then return, and the planet's portrait is renewed. Jupiter's equatorial stratosphere undergoes a repeating wind cycle called the quasi-quadrennial oscillation, where winds reverse direction over a few Earth years. High above the main cloud decks, the air is thinner and more layered, yet it is still stirred by waves rising from below. Those waves deposit momentum as they break, nudging bands of wind to speed up, slow down, and eventually flip. The pattern echoes Earth's equatorial stratospheric oscillations, but Jupiter's tempo is longer, closer to 4 years. The cycle leaves fingerprints in temperature and composition changes that move downward through the stratosphere like slow, descending ripples. A useful sense of place is altitude. These winds live tens of miles above the visible clouds, roughly 30 to 60 miles, or about 50 to 100 kilometers. Jupiter's fast rotation sets the stage, but the stratosphere keeps its own measured rhythm. Even above the storms, the giant prefers repeating cadence over chaos. Jupiter produces X-rays near its poles, and those auroral X-rays reveal energetic particles striking the upper atmosphere. Space telescopes have watched the polar regions brighten in high-energy light beyond human vision. Part of the glow comes from ions funneled along magnetic field lines, colliding with atmospheric gases and releasing X-rays. Another part comes from Jupiter's disk, where solar X-rays are scattered back to space by the planet's upper haze. Because Jupiter's magnetic field is strong and its magnetosphere is immense, its auroras can be persistent and powerful in multiple wavelengths at once. The X-ray pulses can change with solar wind conditions and with the state of the magnetosphere, linking distant space weather to the topmost air. A helpful scale is size. The auroral ovals wrap around polar regions thousands of miles across, on the order of 3,000 miles or about 5,000 kilometers. In X-rays, Jupiter looks like a lighthouse at the poles, lit by particles and fields. A donut-shaped cloud of plasma called the Io Taurus circles Jupiter, created largely from volcanic gases escaping the moon Io. Io releases sulfur and oxygen-bearing material that becomes ionized and trapped by Jupiter's magnetic field. Once charged, the particles are compelled to move with the planet's rotating field, forming a bright ring of electrified matter. The Taurus sits near Io's orbit, about 262,000 miles from Jupiter's center, roughly 422,000 kilometers, and it can glow in ultraviolet light. This plasma is not static. It is replenished, heated, and stirred, with temperatures and densities that shift as Jupiter's rotation and the solar wind reshape the magnetosphere. The torus also feeds Jupiter's radiation environment by supplying particles that can be accelerated and transported. In a sense, Io is a volcanic wellspring, and Jupiter is the magnetic basin that catches the flow. The torus is a visible reminder that moons and magnetism can build structures as real as rings, made not of ice but of charged gas. Jupiter's magnetic field is stretched into a broad magnetodisk because the planet spins fast and flings plasma outward like a rotating fountain. Near Earth, magnetic fields are often pictured as tidy loops. Near Jupiter, rotation dominates, and field lines are dragged into a flattened, disc-like shape by the weight and motion of trapped charged particles. This creates a vast current sheet near the equator, a region where electrical currents flow and the magnetic field direction can change across a thin boundary. The sheet can wobble as Jupiter rotates, like a skirt caught in a steady wind. Plasma supplied by moons, especially Io, increases the mass loaded onto the magnetic field and strengthens the disk-like character. The magnetodisk helps explain why Jupiter's space environment behaves differently from a purely solar wind-driven system. It is a magnetosphere powered from within, not only pressed from without. Think of it as a spinning, invisible engine. Jupiter's rotation provides the torque, the plasma provides the substance, and the magnetic field provides the rails. The size of Jupiter's magnetosphere changes dramatically with the solar wind, swelling and shrinking like a great lung in space. When the solar wind pressure is low, Jupiter's magnetic bubble can expand far from the planet. When the wind is strong, it compresses the boundary inward. A useful landmark is the magnetopause, where the solar wind and Jupiter's field balance. That boundary can sit at roughly 2 million miles from Jupiter, about 3 million kilometers, or it can push outward to around 4 million miles, about 6.5 million kilometers. Inside, particles are guided and stored. Outside, the solar wind streams past with less constraint. This changing size affects auroras, radiation levels, and the paths of charged dust. Spacecraft experience it as a shifting frontier. One day, they might be in Jupiter's domain, another day in the solar wind. The magnetosphere is not a rigid shell. It is a living boundary that breathes with the sun's shifting gusts, while Jupiter's rotation and internal plasma sources keep it energized. Ahead of Jupiter's magnetosphere lies a bow shock, where the supersonic solar wind is abruptly slowed and heated as it meets the planet's magnetic obstacle. This shock is a frontier made of plasma, not stone. Yet it behaves like a wave breaking on an unseen shore. As the solar wind piles up, magnetic fields and particles are compressed and stirred into turbulence. Spacecraft detect the crossing as a sudden jump in particle counts and a sharp change in magnetic conditions. The distance of the bow shock from Jupiter is not fixed because it follows the magnetosphere's own breathing. In broad terms, it can stand millions of miles upstream, on the order of 2 to 4 million miles, or about 3 to 6.5 million kilometers, depending on solar wind pressure. The shock marks where the sun's flowing atmosphere first yields to Jupiter's magnetic presence. It is the opening note in a chain of boundaries that includes the magnetosheath and the magnetopause. Around Jupiter, space itself develops structure, as if the void learned to form weather. Jupiter's auroras include bright footprints that mark where certain moons connect electrically to the planet, and Io leaves the clearest signature of all. As Io moves through Jupiter's magnetic environment, it acts like a stone in a flowing river of plasma. The interaction drives electric currents along magnetic field lines, carrying energy down into Jupiter's polar atmosphere. Where the current arrives, a compact bright spot appears within the auroral oval, and a trailing glow can follow along the oval as the connection persists. This footprint is visible in ultraviolet and infrared, and it can brighten or dim as plasma conditions change. The phenomenon shows that Jupiter's magnetosphere is not just a shield. It is a circuit, with moons as moving components and Jupiter's upper atmosphere as a glowing endpoint. The same general idea applies to other moons, but Io's volcanic supply makes the connection especially vivid. In that polar light, a moon's orbit becomes visible. The aurora writes the moon's presence as a signature on Jupiter's sky. Jupiter's rings become most visible when backlit, because they are made of fine dust that scatters light forward like a smoky halo. Seen from many angles, the rings look faint or even absent. But when sunlight strikes them from behind, countless tiny grains send light toward the observer, and the system brightens. This behavior is a clue to particle size. Much of the material is comparable to smoke, on the order of 10 micrometers across, about 4/10,000ths of an inch. Such small grains respond not only to gravity, but also to sunlight pressure and to electromagnetic forces in Jupiter's space environment. The rings are therefore delicate and constantly renewed, with new dust supplied by impacts on small inner moons. Their faintness is part of their meaning, because it reveals a system dominated by tiny particles rather than large icy chunks. Jupiter's rings are a whisper compared with Saturn's, yet they teach a crisp lesson in light scattering. Backlighting turns hidden dust into a luminous outline, and the giant briefly wears a visible halo. Deep inside Jupiter, pressures rise so high that hydrogen is expected to become metallic, helping generate the planet's mighty magnetic field. Near the clouds, hydrogen behaves as a familiar gas. Descend into the depths, and the weight of overlying layers squeezes it until electrons move freely, as if in a metal. This transition is thought to occur at pressures around 1 million bars, which is about 15 million pounds per square inch and about 100 gigapascals. Under such conditions, matter that seems simple becomes exotic, and conductivity rises sharply. Flowing metallic hydrogen, driven by Jupiter's heat and rapid rotation, can act as the dynamo that sustains the global magnetic field. The idea links the planet's interior to its far-reaching space environment, as if the depths whisper and the magnetosphere answers. Metallic hydrogen is also a reminder that gas giant is only a surface description. Jupiter's true body is a gradient of states, each shaped by pressure. In the deep, hydrogen becomes both substance and circuitry, and the planet's magnetism gains its hidden source. Jupiter's most powerful thunderstorms rise from deep water clouds and build plumes that can disturb whole regions of the surrounding bands. Water is heavier than the gases above it, so lifting it requires strong convection fueled by internal heat. When water vapor condenses, it releases heat and strengthens the updraft, allowing storms to grow tall and vigorous. Clusters of lightning and microwave signatures suggest that some storms originate far below the visible ammonia tops, where water should be abundant. These events can loft material upward and change local cloud colors, leaving bright outbreaks and dark wake regions in their path. Storm clusters can also excite waves that travel along jet streams, reshaping nearby patterns without needing a solid surface. A useful scale is vertical reach. The active layer involved can span on the order of 60 miles in depth, roughly 100 kilometers, from upper clouds down toward warmer levels. Jupiter's thunderstorms are not brief squalls. They are deep engines that convert hidden heat into towering motion, and the bands around them respond like rivers around a rising spring. Microwave observations show that Jupiter's ammonia is not evenly mixed, revealing deep circulation patterns that do not simply mirror the visible stripes. Ammonia is a key ingredient for upper clouds, so its abundance shapes what the planet looks like from afar. Longer wavelength measurements can sense ammonia far below the top haze, because they penetrate where visible light cannot. The results indicate that the equatorial region holds more ammonia, and that this richness extends downward like a deep column. Many mid-latitude regions, by contrast, appear more depleted, suggesting either different vertical mixing or processes that remove ammonia from the upper layers. The pattern implies that Jupiter's atmosphere has deep, organized circulation, not just shallow winds skimming over the top. A sense of depth helps here. The microwave view can probe tens to hundreds of miles below the cloud tops, on the order of 60 to 200 miles, roughly 100 to 300 kilometers. Jupiter's chemistry is therefore a tracer of motion. Ammonia becomes a dye in a vast, invisible flow, helping scientists read the planet's interior weather without ever touching the clouds. Eclipses of Jupiter's moons were once proposed as a tool for finding longitude, showing how the Jovian system offered a portable clock to Earth's oceans. If an observer knew the predicted time of a moon's eclipse in a reference city, then the locally observed time difference could reveal east-west position. The method was elegant because the eclipses were regular and could be predicted with careful tables. On land, it helped coordinate time and refine maps, and observatories compared notes by watching the same disappearances and reappearances. At sea, it was harder, because telescopes and ship motion rarely cooperate, but the idea still pushed navigation forward. The technique illustrates a broader truth. Jupiter's moons form a clockwork that can be seen from far away, and that clockwork once mattered to human geography. The scale is modest in equipment but grand in concept, because the timing hinges on a moon orbiting hundreds of millions of miles away. Jupiter's system became a bridge between astronomy and exploration. A shadow crossing a moon helped chart an ocean. Jupiter's gravity carves gaps in the asteroid belt by setting up orbital resonances that repeatedly tug asteroids at the same point in their paths. The main asteroid belt lies between Mars and Jupiter, roughly 2 to 3.5 times Earth's distance from the Sun. In friendlier numbers, that is about 370 to 650 million miles, or about 600 million to 1.05 billion kilometers from the Sun. Within that region, some orbits fall into simple timing relationships with Jupiter's year. When an asteroid's period matches such a rhythm, Jupiter's repeated gravitational nudges add up, like a gentle push delivered on the same beat. Over long spans, those asteroids can be destabilized, moved to new orbits, or removed from that zone, leaving a gap in the distribution. The result is not a clean, empty ring, but a sculpted structure with missing lanes. Jupiter does this without touching a single rock. Gravity alone can organize absence. The asteroid belt becomes a record of resonance, and Jupiter is the unseen metronome that helps shape it. Jupiter and Saturn meet in the sky on a slow rhythm of about 20 years, and their repeated alignments reflect the steady clockwork of giant planet orbits. Because Jupiter circles the Sun in about 11.86 years and Saturn in about 29.5 years, Jupiter gradually catches up and passes Saturn from Earth's perspective. The interval between close approaches is about 19.9 years, a cadence often called the Great Conjunction. Each meeting happens against a slightly different background of stars, because the planets' paths and viewing geometry shift over time. In ancient records, these conjunctions were noted and tracked as part of longer celestial patterns. In modern astronomy, they remain a useful reminder that planetary motion is predictable and that periods can be combined into larger rhythms. The giant planets set the slow drums of the solar system. Their repeated meetings also hint at deeper gravitational relationships that shape long-term stability. Even without spectacle, the timing itself is beautiful, a reliable return, measured in decades, written by gravity into the sky. Europa's surface is bombarded by charged particles from Jupiter, and that radiation can manufacture reactive chemicals that may mix into the Moon's hidden ocean. The ice is not chemically quiet. Energetic particles can split water molecules, freeing oxygen and hydrogen and enabling new compounds. Over time, the surface can accumulate oxidants, substances that carry chemical energy. If cracks, chaotic regions, or slow recycling transport. Some of these materials downward, the ocean would receive not just water, but ingredients with stored chemical potential. This idea matters because sunlight is weak at Jupiter's distance, and chemical energy becomes especially valuable as a driver of reactions. The radiation comes from Jupiter's magnetosphere, which sweeps past Europa as the Moon orbits, constantly renewing the particle bombardment. The process is a dialogue between space and ice. Particles write chemistry into the surface, and geology may carry that chemistry into the depths. Europa's bright crust is therefore more than a shell. It is a chemical workshop where Jupiter's invisible storms in space help shape what the ocean might contain. Ganymede's own magnetic field creates a miniature magnetosphere, and it interacts with Jupiter's larger field like a small shield nested inside a vast one. Field lines from Jupiter and from Ganymede can reconnect, guiding particles and shaping auroral ovals over the Moon's poles, because Jupiter's magnetic field at Ganymede's orbit changes as the giant rotates. Ganymede's auroras can shift in response, a gentle rocking written in light. By measuring how those auroral positions move, scientists can infer the presence of a conducting layer beneath the surface, consistent with a salty subsurface ocean. The logic is subtle but sturdy. A salty ocean can generate induced magnetic responses that alter how auroras behave. Scale helps ground the picture. Ganymede spans about 3,270 miles, roughly 5,270 kilometers, so its magnetosphere is a planetary phenomenon in miniature, not a minor quirk. It is a moon with its own invisible envelope. In Jupiter's realm, even a satellite can hold a private magnetic domain, and that domain becomes a tool for probing hidden water beneath ancient ice. Callisto orbits far enough from Jupiter that it lies largely outside the harshest radiation belts, making it a comparatively calmer outpost in a magnetic system known for intensity. Distance matters here, because trapped particles thin out with radius. Callisto circles Jupiter at about 0.17 million miles, roughly 1.88 million kilometers, well beyond the inner zones where radiation is strongest. This gentler environment has practical consequences for spacecraft operations and for long-duration exploration concepts, because electronics and materials face less energetic particle damage. Scientifically, Callisto remains fascinating because its ancient, cratered surface preserves early solar system history, while evidence still suggests the possibility of a deep ocean. The Moon's calmer setting does not mean it is simple. It means its story can be read with fewer interruptions from extreme radiation. Callisto sits like a quiet archive at the edge of a powerful field. Around it, Jupiter's magnetosphere still reaches, but with a softer hand. In that quieter region, time and geology have kept their records clear. Stellar occultations by Jupiter let scientists measure the planet's upper atmosphere, because starlight bends and fades as it passes through thin layers of gas. When Jupiter moves in front of a star, the star does not simply blink out. Its light dims gradually, refracted and absorbed along a path that skims the planet's limb. By recording that smooth dimming, researchers reconstruct how density changes with altitude, and from that, infer temperature profiles. The same technique can reveal hazes, wave structures, and subtle layering that are difficult to see in ordinary images. It is a method built on geometry and patience, using a distant star as a steady lamp. A useful sense of scale is the thickness of the sampled region. The key information often comes from the uppermost tens of miles, roughly 30 to 60 miles, or about 50 to 100 kilometers, where gases are thin and responsive to waves and chemistry. In an occultation, Jupiter becomes a lens as well as a planet. Its atmosphere writes a signature into a fading beam, and a distant point of light becomes a probe. A leading model called the Grand Tack proposes that Jupiter migrated inward early in solar system history and later moved back outward, reshaping where the inner planets assembled. In this idea, Jupiter interacted with the young gas disk, trading angular momentum so its orbit drifted. As Saturn grew, the pair could have reversed direction, like two dancers finding a new balance in the same flowing crowd. Some simulations place Jupiter's closest approach to the Sun near 1.5 astronomical units, about 140 million miles or 230 million kilometers, before the outward turn. The key point is not a single number, but the possibility of migration as a creative force. Such motion can scatter planet-building material, mix dry and icy ingredients, and alter the growth of Mars and the asteroid belt. Jupiter, in this picture, is not merely a survivor of formation. It is an active shaper of architecture. Its gravity may have been a sculptor from the very beginning. At the pressure level in Jupiter's atmosphere that matches Earth's sea level pressure, the temperature is about minus 130 degrees Fahrenheit, or about minus 110 degrees Celsius. This 1 bar level is a reference height that gives scientists a familiar benchmark in an unfamiliar sky. Above it, air is colder and thinner, and ammonia more readily freezes into pale cloud particles. Below it, pressure rises smoothly and the gases grow denser, shifting chemistry and cloud formation step by step. Because Jupiter has no solid surface to stand on, this pressure level becomes a kind of coastline on a sea of gas. It is also the level where many comparisons to Earth's weather feel most intuitive, even though Jupiter's ingredients and scales differ. Instruments and models often anchor profiles here, then build upward and downward into the strange. A planet can be measured by landmarks that are not rocks. Pressure can serve as a shoreline, and the 1 bar line is where many comparisons begin. Jupiter's interior structure can be inferred from tiny variations in its gravity field, and Juno measured those variations by tracking minute changes in its radio signal during close flybys. As the spacecraft sped past, regions of slightly higher or lower mass tugged it, shifting the frequency of the transmitted tone by a hair. From these shifts, scientists refined Jupiter's gravitational harmonics, a mathematical description of how mass is distributed with latitude and depth. The closest encounters skimmed roughly 3,000 miles above the cloud tops, about 5,000 kilometers, close enough for gravity's fine texture to be felt. Those measurements help constrain whether heavy material is concentrated or mixed, and how deep the winds extend before the planet's interior rotates more uniformly. The method is quiet and elegant, like reading a drum's shape by listening to its pitch. Jupiter answers not with rock samples, but with the way it pulls on a passing craft. Jupiter is noticeably flattened by its rapid rotation, and the difference between its equatorial and polar size is a direct clue to its fluid interior. The equatorial radius is about 44,400 miles, roughly 71,500 kilometers, while the polar radius is about 41,700 miles, around 67,000 kilometers. This bulge is rotation made visible. A spinning, mostly fluid body cannot help but swell at the waist. The amount of flattening depends on how mass is layered inside, because denser material resists reshaping differently than lighter material. That is why the planet's silhouette is not just a geometric curiosity, it is a constraint on interior models, linking the visible outline to deep physics. Even Jupiter's winds feel the consequences, because a broader equator changes the paths and spacing of jets. Here, shape becomes a diagnostic tool, not just an aesthetic. Jupiter's profile is a record of speed, weight, and softness, written into the curve of a giant made mostly of gas. Jupiter's equator shows a repeating chain of bright plumes and darker hotspots, and this pattern is tied to a large atmospheric wave traveling around the planet. The darker hotspots are regions where reflective high clouds are thinner, so deeper warmth escapes more freely, while bright plumes mark upwelling zones that build fresh cloud tops. Many researchers interpret the sequence as a Rossby wave, a vast meander in the flow created by rapid rotation and changing latitude effects. The hotspots can span about 1,000 miles across, roughly 1,600 kilometers, large enough to be tracked for weeks as the pattern marches onward. A wave like this does not just decorate the sky, it organizes convection, shapes where clouds form, and steers smaller storms like a current guiding driftwood. Jupiter's atmosphere becomes legible when a wave writes in repetition. The equator is not random turbulence. It is weather arranged into a recurring sentence. Deep in Jupiter's troposphere, water is expected to condense into clouds at pressures of several bars, and that hidden water layer powers some of the planet's most vigorous storms. Water vapor rising from warmer depths cools as it expands, then condenses into droplets and ice, releasing heat that strengthens the updraft in a self-feeding loop. Because water is heavier than the gases above it, lifting it demands strong convection, so these storms can be intense once they begin. Many models place the main water cloud region around about 6 bars, near 90 pounds per square inch, or about 600 kilopascals. From there, towering convection can loft material upward into colder layers, affecting colors and cloud textures seen from afar. Lightning and radio signatures hint at this deep engine working behind the brighter ammonia haze. Jupiter's internal heat is the quiet heavyweight, driving storms from depths that sunlight barely reaches. In a world without land, water still finds a way to gather, rise, and fall. The pressure at Jupiter's center is so extreme that it reaches tens of millions of bars, forcing matter into states that have no everyday counterpart. Interior models commonly estimate central pressures around 40 to 70 megabars, and a mid-range value of 50 megabars is about 725 million pounds per square inch, or about 5 terapascals. Under that weight, atoms crowd together, electrons move more freely, and the familiar boundary between gas and metal dissolves. This is the realm where hydrogen becomes a powerful electrical conductor, and where helium may separate in ways that reshape the planet's composition over time. The sheer pressure also means heat is stored and transported differently than in rocky planets, because compression and conductivity dominate. When scientists talk about Jupiter's depth, they are often really talking about pressure. It is a world built from weight itself. Jupiter's center is not a place you could stand. It is a deep physics laboratory where gravity presses matter into new rules. Jupiter's interior is thought to be thousands of times hotter than its cloud tops, with models suggesting temperatures of tens of thousands of degrees near the deep center. Estimates often fall around 20,000 to 30,000 kelvins, comparable to about 35,000 to 50,000 degrees Fahrenheit, or roughly 20,000 to 30,000 degrees Celsius. This heat is sustained by leftover energy from formation and by slow gravitational contraction, a steady settling that releases warmth over billions of years. Temperature matters because it sets buoyancy, and buoyancy drives convection, the broad overturning that transports heat upward. It also influences where different materials mix or separate, shaping the planet's internal layering. When combined with immense pressure, high temperature changes the behavior of hydrogen, helium, and dissolved heavier elements, turning the interior into a dynamic, conducting ocean. Jupiter may look cold at the top, but its deeper layers remember their birth. The outer chill is only the skin of a planet with a fiery interior memory. Jupiter emits a steady radio glow called synchrotron radiation, produced by near light-speed electrons spiraling through its powerful magnetic field. This is not a brief burst, but a persistent beacon that radio telescopes can map. Much of it is studied at wavelengths of a few centimeters, for example, about 5 inches or about 13 centimeters, where the belt-like emission stands out clearly. As electrons curve along magnetic lines, they radiate, and the brightness reveals where energetic particles are trapped and how the field guides them. The emission is strongest in broad belts around the planet, forming an invisible halo that mirrors the magnetosphere's shape. Changes in intensity can track how particle populations rise and fall with the solar wind and with plasma supplied from moons. Jupiter speaks in radio with a steady voice, and the data turn invisible motion into a readable map. Juno revealed that Jupiter's magnetic field includes intense localized structure, including a concentrated region nicknamed the Great Blue Spot. Instead of a simple bar magnet shape, Jupiter's field has patches where strength and direction change rapidly over short distances. The Great Blue Spot lies near the equator and marks a compact region of unusually strong magnetic intensity, suggesting complex flow patterns in the conducting interior. Juno's magnetometer mapped these features during close passes only about 3,000 miles above the clouds, roughly 5,000 kilometers, where fine structure could be resolved. Such detail implies the dynamo is not a smooth, uniform engine. It is a shifting tapestry of currents, likely influenced by how heat, composition, and rotation interact deep within metallic hydrogen. Magnetic maps become a kind of interior weather report, but written in invisible lines. Jupiter's field is not just a shield. It is a changing fingerprint of motion deep below the clouds. The Great Red Spot has been observed to shrink over the last century, showing that even Jupiter's most famous storm evolves on human timescales. Historic drawings and measurements suggest a larger oval in earlier eras, while modern images show a more compact vortex. In recent decades, its long axis has often been around 10,000 miles, about 16,000 kilometers, still larger than Earth but smaller than its past extremes. The cause of the shrinkage is still studied, and likely involves changes in surrounding jet streams, energy supply from smaller vortices, and how turbulence cascades in a rotating fluid. The storm remains an anticyclone, with high-speed winds circling a calmer center, and its reddish hues still hint at complex chemistry shaped by sunlight and depth. Shrinking does not mean fading into insignificance. It means the atmosphere is alive and responsive, even at monumental scale. On Jupiter, longevity does not require stillness. The red spot endures by adjusting its size like a heartbeat measured over decades. Jupiter's atmosphere is enriched in several heavier elements compared with the Sun, and this chemical surplus is a clue to how the giant planet formed. Measurements show that elements such as carbon, nitrogen, and sulfur appear at higher abundances than a simple solar mixture would predict for pure captured gas. One explanation is that Jupiter accreted icy and rocky planetesimals while it was gathering hydrogen and helium, adding solids that carried these elements inward. Those solids are most readily available beyond the young solar system's frost line, often discussed near about 3 astronomical units, around 280 million miles or 450 million kilometers from the Sun. In that colder region, ices can lock up volatile elements and deliver them efficiently to a growing giant. Chemical enrichment is therefore a fossil signature of building materials, not merely a present-day ingredient list. Jupiter's clouds are not only weather, they are history, stirred but not erased. Jupiter's main cloud layers form at different pressures because different compounds condense at different temperatures, creating a vertical map of chemistry. Near the upper troposphere, ammonia freezes into pale ice particles around roughly 0.7 bar, about 10 pounds per square inch, or about 70 kilopascals. Deeper down, near about 2 bars, ammonium hydrosulfide is expected to condense, near 29 pounds per square inch, or about 200 kilopascals, and it can help darken some belts. Deeper still, at several bars, water condenses into thick clouds that feed thunderstorms and lightning. These are not rigid layers like floors in a building. They overlap, shear, and mix as winds slide past and convection punches upward. Yet the condensation points still matter because they set where certain cloud types can exist and where latent heat is released. Jupiter's palette is tied to this vertical structure, with brightness and darkness linked to altitude and chemistry. The planet's sky is a stratified cookbook, with pressure as the oven dial. Europa's surface contains regions called chaos terrain, where the ice looks disrupted into jumbled blocks that appear rotated, tilted, and refrozen. These landscapes suggest that the shell has, at times, been warmed or weakened from below, allowing segments of crust to shift before locking back into place. One leading picture is that buoyant warm ice or briny water rose upward softening the underside of the shell and making it behave like broken sea ice. As the material cooled again, it froze into a patchwork that preserves motion as geology. Individual chaos regions can span hundreds of miles, for example, about 200 miles across, or about 320 kilometers, large enough to be mapped as distinct provinces on the Moon. Chaos terrain matters because it may mark places where the boundary between ice and ocean becomes more interactive. It is a reminder that Europa is not a static ice ball. Its crust has learned to rearrange itself, quietly and dramatically, under Jupiter's tides. Europa's long double ridges likely form when tidal stresses open fractures that fill with slushy water or warm ice, which then freezes and builds raised walls on either side. As Europa orbits Jupiter, repeated flexing pulls the crust, sometimes cracking it like a sheet of ice under shifting load. When a crack opens, buoyant material from below can rise, freeze, and expand, pushing the surface upward along both margins. Repeated episodes can widen the structure and add smaller ridges nearby, creating braided networks that stretch for great distances. Some ridge systems run for hundreds of miles, such as about 600 miles or about 1,000 kilometers, tracing arcs across the bright plains. Their geometry records stress patterns, showing where the shell was pulled apart and how it healed itself. In this slow construction, Europa's surface turns invisible tides into visible architecture. Jupiter's gravity can sculpt landscapes without fire, using flexing as its chisel. Io is wrapped in a vast cloud of neutral sodium, visible from Earth as a faint yellow glow that extends far beyond the Moon's immediate vicinity. Volcanic eruptions and surface sputtering release sodium-bearing compounds, and sunlight and charged particles can break these molecules apart, freeing sodium atoms. Once loose, the atoms spread into a broad envelope and can be pushed by sunlight, forming extended tails and streams. The sodium cloud can grow enormous, reaching hundreds of thousands of miles across, for example, about 400,000 miles, or about 650,000 kilometers. Some of this material becomes part of a larger neutral torus around Jupiter, and some is ultimately ionized and swept into the magnetosphere, where it can help feed radiation belts and auroras. Io, in this way, exports its volcanism into space. A moon can make a planet's environment richer and more complex. In Jupiter's realm, even a thin cloud of atoms can become a bridge between geology and magnetism. Amalthea has a surprisingly low density that suggests it may be porous and ice-rich, even though it orbits close to Jupiter, where conditions are harsh. The Moon is irregular and reddish, shaped more like a rugged stone than a sphere, and it circles inside regions of strong radiation and powerful tides. Yet its measured mass and size imply a density below that of liquid water, consistent with substantial ice or a rubble-like interior filled with voids. Amalthea is about 155 miles long, roughly 250 kilometers, but it carries a story larger than its shape. Such low density hints at gentle assembly or a captured origin, and it raises questions about how icy material could survive so near a giant that radiates heat and traps charged particles. Its surface may be continuously weathered by impacts and radiation, yet the interior can remain a quiet archive of composition. Amalthea shows that proximity does not always mean simplicity. Near Jupiter's glare, a small moon can still be fragile and enduring. Metis and Adrastea are tiny inner moons that help sustain Jupiter's main ring by supplying fresh dust through constant micrometeoroid impacts. These moons orbit just above the cloud tops, where Jupiter's gravity is strong, and the ring particles circle at high speed. When small impacts strike their surfaces, grains are knocked free and spread into ring-like paths, continually renewing a system that would otherwise disperse. Their sizes are modest, with Meteor about 25 miles across, around 40 kilometers, and Adrastea smaller still, yet their contribution is outsized. Dust production links solid bodies to the delicate ring, making the ring a living exchange between rock and orbit. The grains feel not only gravity, but also subtle forces from sunlight and plasma, so the system is constantly being rearranged even as it is replenished. These moons are like quiet quarries in motion. They shed material, the ring gathers it, and Jupiter's gravity holds it in place as a faint, persistent band. Jupiter's halo ring is thicker than its main ring because fine dust grains become electrically charged and are nudged out of the equatorial plane by electromagnetic forces. Tiny particles pick up charge from sunlight and from plasma in Jupiter's magnetosphere, and then respond to the rotating magnetic field and associated electric fields. This can tilt and warp their orbits, spreading dust above and below the plane that larger particles prefer. The halo sits inward of the main ring and occupies a region close to the planet, roughly from about 57,000 to 62,000 miles from Jupiter's center, or about 92,000 to 100,000 kilometers. Because the grains are small, they are more easily stirred, and the result is a diffuse three-dimensional component rather than a flat ribbon. In photographs, the halo looks like a soft glow, but it is shaped by rigorous physics. Here, electricity joins gravity as a sculptor. The ring listens to Jupiter's magnetic voice, and the halo becomes a three-dimensional whisper in motion. Jupiter's apparent size in Earth's sky changes substantially over time, mainly because the distance between the two planets varies as they follow their orbits. When Jupiter is on the far side of the Sun, it appears smaller. When Earth passes between Jupiter and the Sun, the planet comes closer and looks larger and brighter. At a favorable opposition, Jupiter can be about 365 million miles away, roughly 590 million kilometers, while at conjunction, it can be well over 600 million miles, about 970 million kilometers. The changing distance alters not only brightness, but the amount of detail visible through a telescope, because the disk grows or shrinks in angular width. This variability is a gentle reminder that the night sky is not a fixed dome, but a moving geometry. Jupiter's stripes, spots, and moons are always there, yet our perspective slides closer and farther like a slow tide. The planet's grandeur is constant, but the viewing window breathes with orbital mechanics. In that changing view, Jupiter reveals itself as a set of moving circles, each one altering the scene from Earth. Jupiter has taken us through a world where clouds are not merely weather, but architecture, and where gravity is not merely force, but a quiet author of patterns. We've watched how a planet made mostly of hydrogen and helium can become a place of metallic depths, electric fields, and auroras that write light across polar night. We've met storms that outlast centuries, belts that vanish and return, and waves that arrange the equator into repeating sequences. We followed moons that are each a distinct story. Io, where tides become volcanoes. Europa, where ice becomes a map of hidden water. Ganymede, where a moon carries its own magnetic shelter. Callisto, where ancient impacts keep their record. In Jupiter's realm, Even dust learns choreography, shaping faint rings and racing outward in charged streams. And as the giant turns, fast and steady, it reminds us that scale can be gentle. A larger world does not have to be harsher. It can be more patient, more rhythmic, more spacious in the way it holds its secrets. Jupiter shows how the solar system is stitched together, by resonances that keep moons warm, by migrations that may have guided the early planets, by a magnetosphere that breathes with the solar wind, and by a brightness that has guided human eyes for centuries. If you have grown sleepy while traveling these facts, let that be part of the learning too, because Jupiter itself is a teacher of slow endurance. Sleep well. Good night.